In this topic, we will cover what we call a pole and beam analogy for understanding voltages and megavar characteristics in networks. So through this analogy, we would like you to be able to describe how voltages and megavars in a network interact. We would like you to actually use this analogy in real-time situations to identify weak buses in your system and strong buses. Anticipate how bus voltages will vary as we add inductive capacitors and megawatt loads to your network. Anticipate how voltage collapse may occur. Anticipate when you may need to have megavar reserves and when you may be deficient. Determine the best locations for dispatching those megavar reserves. Also anticipate severe overvoltages and anticipate the isolating effect of having generators in your system. Currently, there are two popular analogies for megavars. One is the foam on the glass of beer. Basically, the analogy is that the megavars flowing in a transmission line are the foam, the megawatts are the actual beer, and basically the megavars are a nuisance. They basically fill up the glass with current, and they just get in the way of the true goal, which is to drink the beer, which is to move the megawatts. Now, that analogy will only take you so far when you're on the job. In fact, if anything, it may be a hot summer day, you may be running under different conditions, you may be really wanting to get off shift and have that glass of beer. But really, that analogy is not going to help you in any way make a good decision about how to run your system. The other analogy is the wheelbarrow analogy, and that is that you basically have to lift the wheelbarrow a certain amount to move it in the direction you want to go. So the real work you're doing is moving that wheelbarrow with the load, but you've got to put a certain amount of energy into it to do the lifting. And again, this analogy will only take you to a very limited distance in terms of making real decisions. So we have a proposal, and we call it the pole and beam analogy. Basically, the analogy is that the generators are analogous to these cable lifters, and they are lifting these poles. The generators have a megavar contribution, and as they lift those poles, and let's say it's a 230 kV system, you want that generator to keep that megavar right at 230 kV. That's analogous to the cable lifter keeping his pole right at, say, 23 feet. Now, if that cable lifter hits his maximum lifting weight, let's say we double, triple the weight that's on that, what's going to happen to that cable lifter? He's going to sag on down. That is analogous to the generators not being able to maintain their voltage. When those generators hit their megavar limit, they start to sag on down. And you can start to see the interacting effect. In the pole analogy, as one cable lifter drops on down, think what's going to happen. If this guy comes on down all the way to here, instead of sharing the load between this lifter and this lifter is going to have the entire weight. So that's the impact. When one generator hits its megavar limit, the other generators have to pick up that load. And I actually like to use the analogy is that these are more like strong, flexible steel bands rather than cables. All right, a cable would actually have a curve like this. So you remember how we used this with the whole issue with voltage collapse. It's like this beam is anchored solidly at one end, and as we apply a load, it drops on down like that. So that's the mental model I want you all to have. And so basically, this is what we would call a relatively weak bus, that we're getting a significant drop across those transmission lines. So these beams here are like the transmission lines. The longer the transmission line, the greater the impedance, then the weaker and longer that beam is. So a strong bus is when we have when we're close to what we call a dynamic megavar source, and the voltage doesn't change significantly as we add load. So a strong bus is like we have a very short distance, okay? We can be adding a load here, but our transmission line is very short. It has a low reactance, and we don't get a lot of sag as we add a different force. A weak bus is when we have a very long line, we have very high reactance, and we get a lot of sag as we come on down. So this is an example of a weak bus. We have a lot of sag. We have a relatively weak beam coming across. Here's a case where we have a very strong bus. We've got the big sumo wrestler, but he's on the high dive board, which is very thick. As that sumo wrestler goes on out to the end of that short, thick board, there's going to be very little sag. But again, if the sumo wrestler was on the low dive, which was a long springy board, you can imagine the amount of sag that would happen. And this is an example is that pretty much on Google, you can find anything. If you Google sumo high dive, then you can actually get something in today's world. So here's a case where we have our two lifters, and we have a much stronger bus, and we see that the amount of sag that is happening due to that weight is much less. And in this particular case, they're both sharing the amount of load. Now, the analogy we have for shunt capacitors is they are like a blimp that actually lifts the voltage. And this shows the fact that two capacitors, or two blimps the same size, when they are lifting a part of the roof that is close to the poles, then we have very little voltage rise. But it's really important to understand that you may have a low voltage situation, but it's in a very weak part of your system. You apply that shunt capacitor, you could go from 92% to 120% voltage, just like that, all right? So it's really important for you to understand the relative strength of the buses throughout your system. And the strength of that bus is basically, it's a function of the amount of reactance between that bus and the closest generator that is able to regulate voltage. All right? So you understand that reactance. Another way to look at it, in engineering terms, we talk about the short circuit capability. If you applied a fault on that bus, how many megavars would be flowing from that generator to serve that fault? So basically, the change in voltage for a given amount of megavars goes up as the short circuit rating goes down, right? So again, that whole thing is and you can look at your diagrams, you can look at the reactances, but it's important for you to understand for each bus in your system which generators are really serving the megavars and are helping control the voltage at that point. That becomes the anchor point. And that's an important thing, is that it's only your generators or your static var controllers which are providing those anchor points. Your capacitors can make a big difference, but they don't anchor the voltage. They really just raise the voltage with respect to the other anchor points throughout your system. So we had a case where that was the case with the blimp. We moved that to a case where we have generator buses. So our generators are anchoring our voltage at all these points to close to the nominal value, and then we apply our capacitors, and they have the impact of raising the voltage throughout the system. It can actually be beneficial to apply capacitors close to your generators. You may not raise the voltage much, but what you'll do is you'll take that generator, which may have been producing megavars, and by adding the capacitor, you will actually move that generation down to the point where it may be more neutral. It's neither consuming or producing. And so that means by adding the capacitor ahead of time, that generator has more room to produce megavars when you have a line outage. So it's important, again, to kind of use your capacitors strategically. And again, think ahead, not just look at the voltages right now. Think ahead about what's going to happen as you have major contingencies on your system. So here's an example with the reactor. The reactor has the effect of dragging the voltage on down. And again, the amount that that reactor will drag the voltage down will depend upon how strong is that bus, which is a function of how close is that bus to your nearest generator, which has voltage regulating capability. When that generator hits its megavar limit, it's like the pole, it's like the lifter, it's sagging, okay? So that generator has to be within its megavar limit to be able to nail that voltage at the particular set point. So you'll hear about, with operators, things like weak bus, strong bus. To me, with a career in electrical engineering, I'd never heard that term, right? But when you deal with operators, it's an extremely important concept, and what it means is it's the amount that, it's how close is that bus to the nearest generator that is regulating the voltage. And when you have a weak bus, you can have very significant voltage deviations, either high or low, depending upon the megavars you're adding. So in the case with the reactor, our voltage profile is analogous to applying the weights. Again, our generators are nailing the voltage at the set point, but the reactor drags on down the voltage and lowers it below the nominal value. So if we go through the comparison, the height of the top of that pole from the lifter is the voltage on that bus. Your generators, the lifters are like generators. They are ideally anchoring the voltage profile throughout the system. Another way to look at it is you've got this huge tent. You've got your generators strategically placed around the circumference of this tent, and they're all keeping the tent with their poles at a certain height. And you really want them to all keep it at the exact same height. The lifting force on that pole in the upward direction is the megavar output of that generator. Once that generator hits its megavar limit, it can no longer nail that voltage, and that voltage will start to sag. As that voltage starts to sag, the other generators are going to have to pick up more megavars, just like the lifters adjacent to that one that's sagging is going to pick up more of the force. So the lift is controlling the height of that pole. The automatic voltage regulator is controlling that kV set point, as long as we're within the megavar capability of that generator. The metal bands between the poles that are suspending the loads or the reactive loads are like the transmission lines. The longer that metal band, the more deviation you get. The lower the voltage of that transmission line, the longer that transmission line, the more deviation you'll get for applying a voltage at that end. The most stable situation is to have a lifter at both ends, one at this end, one at this end, and then the voltage is only sagging in the middle, okay? But when we have a radial transmission line, you don't have voltage control at that end, so it's like a lifter at one end with the beam sagging significantly. So wherever you can, make sure you've got good support throughout your system, and you have to make sure that those generators keep their units on in automatic AVR mode. And time and again, you'll see in the standards, if a unit is coming off, they have to tell the system operator, because that can have a dramatic impact on voltage stability. In fact, the maximum power you can move across this line is a function. If you have voltage at regulation of both ends, you can move that line to 90 degrees. And then you can have another line and another line, okay? Each running at 90 degrees. But as soon as you lose the voltage regulation at a midpoint, you will get voltage instability, because instead of having 90 degrees between here and here and 90 between here and here, you're going to end up with 180 between here and here, and that will cause voltage collapse. So just the mere fact that that generator takes its AVR off of voltage regulation can give you instant voltage collapse. So it's an extremely important thing to kind of stay in sync with your power plant operators and have them alert you if for some reason that unit's going to hit that limit or it's going to take the voltage regulation off of control. So the weights on this metal band are a combination of the megawatt and megavar loads. A weight close to the pole is analogous to a very strong bus. A weight distance from the pole is like a very weak bus. The blimps are like the shunt capacitors, And voltage collapse is basically just a whole chain reaction, all right? One generator hits its megavar limit, its voltage sag. Another generator has to pick that up, it hits its voltage limit. And so it's like a collapse of a tent, where finally one lifter starts dropping, okay, and the neighboring lifters, they start dropping, and literally over a period of time, you can think of that a whole section of that tent could collapse. Now, it's possible then, and we had this in the 2003 August blackout, we saw 60 million people go in the dark in the northeastern part of the system, and it literally was that analogy. You can look at where the system stayed up, and they had big, strong generators were holding the voltage at that point in the system, but then the rest of the system that went into a major voltage collapse. And actually went through a whole series, but there was a point there where all the generators around the Cleveland area were hitting their megavar limits and collapsing, and we had overloaded transmission lines, and so the whole voltage collapse phenomena was very much integral to that. So I'm hoping that this can actually help you picture an actual system condition. We've got some scenarios on the Palco case where you will see that over a period of time, we have the LOCA system, which is really nailing the voltage on the eastern part of the system, but we see all the generators in the middle and the western part start hitting their limits, and the system goes into a collapse where we have plenty of megavar reserves at LOCA, but the rest of the system is hitting its limits. And so this analogy is also good because megavar reserves have to be in a certain place. Think about the mental analogy. If you have a few weak lifters in one part of your tent, they could very much let that part collapse, but the rest of the lifters with plenty of megavar reserves could be maintaining their poles and their height at other parts. So really, with voltage collapse, any part of your system can take you down in a certain area of the network. So unlike megawatt reserves, which you can pretty much move megawatt reserves across the system, megavar reserves are very local. You really have to get an idea of what's happening in each local part of your network. Each network is somewhat different, and you really have to be watching the alarms coming in and being in tune with the megavar reserves on your generators, because that's analogous to those lifters having the strength to keep that voltage at a certain level. And it can change like that you can be just fine, but then you have some outages, and all of a sudden generators are hitting their megawatt limits, their megavar limits, and the voltages are dropping. So to review, we've described a pole and a flexible beam analogy. We're hoping that through that, especially as you get into the simulation and then you get into running the real system, you'll be able to identify weak buses, strong buses, anticipate how their voltages will vary as you add capacitive and inductive resources, as you add megawatt loads. Those megawatts flowing through the transmission lines are like putting huge weights on the middle of those lines. They are sagging the voltage at the middle of that line, okay? If it's suspended at both ends, you're keeping it up. But if it's suspended at only one end, you're getting a large dropping effect through feeding radial loads. So through this, we hope you'll be able to understand ahead of time where your system may be vulnerable to voltage collapse. Keep an eye on where you have megavar reserves with your generators, and also, of course, know where all your capacitors are in your system. Know where all your inductors are. You really want to make sure all those reactors are off if you are having some megavar deficiency problems, and determine the best locations for switching those devices. And you can also use this. We've had cases where especially during storm conditions, or restoration, you have only a small number of your lines in service. Those voltages can be much weaker than they would be under normal conditions. And so under those conditions, you've got the resistor saying, well, let's just put a big 50 megawatt capacitor on there if my voltages are getting low, because as I've shown, you can go from a very low voltage to a very high voltage in a very short, just instantly. And you'll see cases in the simulation where you'll get that level of variation. And this should help you anticipate the isolating effect of generators. let's say I've got a network and I have a ring of generators. No matter what I do inside of that ring, it's going to have very little impact on the ring on equipment outside of that ring. Those generators have that isolating effect. That there's no way, even if I apply a very large capacitor here, if I have a generator in, but let's say I have a low voltage problem way over here, I have a generator, I can't be affecting that voltage over here because whatever I do here to vary the voltage is going to be negated by that generator holding its voltage at a constant level, and kind of, if I add more megavars here, I'm going to absorb them from the generator. And that comes back to the rule we talked about. Megavars don't travel very far because those generators provide isolating points that really stop those megavars traveling through that control point. So really, it's a new type of analogy, but I hope you'll work with it on the simulator, and at some point you could actually use it to make some good decisions on a real system. Thank you.